In this video, I'm going to show you how to generate the data used in the perceptron training and testing. And here we using MATLAB as a demonstration. Of course, you are welcome using other language or software like C, C++, Python, etc. And here using MATLAB as example. And first, let's click the new script so you can open a new file editor. And I have a good habit is whenever I writing any new code, first I'd like to type in the clear and close all. That can clean the memory and also close all opening window. And then you can add in some notation for yourself. And this part define useful parameters. So as we mentioned in previous video, we know the radius for each of the half moon equal to 10. So let's define the RAD, radius equal to 10. And let's give some notation here. And we know the width equal to 6. WIDTH equal to 6. And now we know the distance between these two half moon equal to 1. So we can define this equal to 0.5. Since for each of them, the distance from that one to the 0 coordination, that equal to 2.5. So here, let's see, we are going to generate 2,500 data. So the total number equal to the number of samples equal to 2,500. So this is the total pixels, total samples we generated in this code. Okay. Now look at think about this two half moon pattern. You know, they are on a two-dimensional plane, x1 and x2. Therefore, we need to define a two-dimensional matrix. So let's give the AA equal to random 2, and then is the number of sample over 2. Okay. The random, this command in MATLAB, let's can generate a random number. The number value is between 0 and 1. So here we can give an example. For example, give the random 1 and 10. That means we want getting 10 values. They are in a one vector. So here they are on the one vector. It's one row by 10 columns vector. So the value between 0 and 1. So look at it here. Look at these 10 variables. The value is the maximum equal to 0.8 and the minimum equal to 0.1. So here, if you give this guy, you can check their size. You can check the size AA. That's equal to 2 and 1250. That is the matrix size. And then let's see the radius equal to read minus so here is, look at our slice. I can show our slice one more time. So from here you can see basically from the center to this edge, that's equal to 10, correct? This is the radius equal to 10. And then this is the width. You can change the color using green color. So from here to here, that is radius minus width over 2. And from here to here, that is radius plus half over width over 2. So let's can explain why we need to have this one. So that is why we have this guy, okay? And then let's define two classes. For class 1, that we give an angle theta 1 equal to y1 equal to radius theta 1, and then we were going to explain what's going on here. Okay, let's explain what's going on here. Let's go back to this figure and see what this means. So I will use in the green color. So here, this is the center of the half moon, for example. Let's look at the red color first. And we know this is their radius, that is equal to 10 or 10 plus that value. And then here from this coordination, this will be the angle, correct? So at this edge, this is 0, so this edge will be equal to 20 degrees. We give a rotation. And then this is the whole angle from here to here. That's equal to the 20 plus the theta, right? And then next thing is we want to convert from the polar coordination to the Cartesian coordination. You know, we know the angle, we know the radius, and then we can find their coordination on x1 and x2. So on x1 is the r multiplied with cosine theta, for example, this is theta. And then for the x2, this is for the x1. And for x2, that's equal to r and the sine theta. So that's we can use in cosine and sine, convert the polar coordination into the Cartesian coordination. So that's the, what the code, what we do in there. So you can see this is the theta, this is the angle. And then this is the radius multiplied with cosine, that's corresponding to the x1. And here we divide the y1, that is x2. So that's radius multiplied sine function. And for the red color, the value all equal to 1. That's using the 1 multiplied with their size. And let's give a try and save the code. And let's give a name called the data generator. We save it. And then, oh, what's going on? The once. This is will be once. Okay, now we have all the data. Let's see what's the size of x1 and the y1. Okay, and the label, label 1. Okay, they are on the same size. So if you look at all the values, you can see x1 is their x1 coordination, and the y1 is their x2 coordination, and the label 1 is our 1. Okay, this is we getting the first half moon. That's the red part. We get this part. Now we need to get in the blue part. Okay, then for the blue part, very similar to the red part, but we need to change a few variables here. For class 2. So here's theta 2. The first one for the red one is we do this rotation, 20 degree. This one is negative 20 degree, so we give a minus 20 degree. And then of course the theta will be equal to minus theta. And then for the first one, on the x it's plus the radius, RAD, and on the y will be minus the distance. So then here will be equal to 2. And here equal to 2, and the label equal to 2. That is always minus 1. Let's give this one. It's minus 1, x2. So here, that's the reason we need the sample over 2, because we generated twice. One is for class 1, another one for class 2. So that's the reason we need a half of the total samples. And let's take a look of the code. Okay, I think it's go through. And then next is we put them together. This is our total data. So adding data together. So we can get in the data 1. The data equal to x1, x2, y1, and y2. Here's a label 1, label 2. So now we have a matrix data. Let's look at the data size of data. So equal to 3 and 2500. Let's check each of them. So for example, we look at the data 1. So that's equal to the first one is x1 and x2, and here is their labels. And then of course we can plot them together and take a look. This part is to display the data. So we do for I equal to 1 to 2500, total number 2500, and x equal to 1, and the data 1 to 2, and II, and the y equal to data 3 and II. So let's give a try. So what this mean? And if II equal to 1, and look at it here. The x will equal to their coordination, and the y will equal to their label. Okay, now let's plot them. If y equal to 1, we're using red color to plot it. Let's plot x2 and x3. We're using red color, red stars, and we let their line width equal to 2. And their macro size to 9. Let's give a little bit bigger bunker size. And else, if y equal to -1, we can plot in a blue color. And then hold all of them. Let's take a look what the plot looks like. Okay, this is exactly what we planned for our data. So basically there's two groups. Group 1 is on red color and group 2 is on blue color. Okay, and we can make it relative, give a better label. So you can see here is HH equal to X LABL label. We call that one is the X1, right? X1. And we set HH font size equal to, give a little bigger, 26. And the font weight equal to bold. Similar, we can set up the X2 label. X2. And we can make the whole GCA relatively larger, give it the bold size label. It's GCA. And you can get in the grid. You can set up the grid, makes it looks more clear. Now we can take a look at the result. Okay, this is what you're going to get. Of course, here you can change it a little bit. Here we give it a rotation 20 degree. Remember here we give it 20 degree. If you can change other value, for example, give it 0 degree, there's no rotation. You can look at the result. Now here is the regular one. There's no rotation, just the two half moon, two half moon. So you can see from here, the center 0, 0 to 0, 0. That is the 10. That is the radius, and here the width equal to 6, and distance between these two is equal to 1. It's pretty close. So after this, we can save the data for the next step. So we can save data and data, and run the data. Okay, look at it here. You have a new file. The file name called the data.match. Now you have the new data saved here. So this data used as the training and the testing purpose. In next video, I'm going to show you how to construct this multiple input, single output perceptron.